Good evening, students. I hope you're able to see my screen and also hear me.
Yes, sir.
So I'll get started. So we started with mechanical properties of solids last class. So just discuss some basic terminology that are there. First is I explain what is deforming force. You need to understand what is elasticity. Plasticity is exactly the opposite of elasticity. Then we saw a technical term called as stress. Stress is defined as a restoring force within the material per unit area. So restoring force per unit area is called as stress. Then we saw the types of stress, which is called as tensile stress, compressional stress, and hydrostatic stress, and tangential or shearing stress. So these are all the terms that we have seen. Right. Similarly, I explained another important term which is called as strain, which is defined as the ratio of change in dimension to the original dimension. Then we saw the different types of strain, which are longitudinal, volumetric, and shearing strain. Right. So these are all the concepts we have already seen. So the continuation of this is something called as elastic limit. So write down. So the next is we are going to discuss the term elastic limit. So as the name suggests, what do you mean by elastic limit?
Maximum elasticity of an object.
Yes. So it is a maximum stress. Okay. So who is causing the who is actually testing the elasticity of a material? It is the stress. So the maximum stress within which, so what happens in stress? There is, see, stress will generate strain. Remember this, guys. Stress is the force that we apply, and there is a deforming force that will come. Due to stress, what will happen? There will be strain. Strain is change in length, area, or volume. So maximum stress within which the object regains its original shape, and size. Correct? So maximum stress within which the object regains its original shape and size after what? After removing the deforming stress, or you can call it as deforming force. After removing the deforming force is called elastic limit. Am I clear, guys? That is, again, imagine a rubber band. Let's say the original length of the rubber band is L, and you have applied a force in both the directions. What will happen is, let's say this side it has got increased by distance L dash. This side also it has got increased by distance L dash. So the total increment that has taken place is L dash plus L dash put together on both the sides. So once you remove these forces, what should happen? If that material is able to come back to its original length of L, then the force that you have applied is within the elastic limit. Am I right? So there will be a particular force beyond which what will happen is the object will not be able to come back to its original length L. Rather, there will be a complete setback that would have happened. Means the material would have changed its dimension. It might sometimes stop at a distance greater than L. Sometimes this will happen. Means the object has got completely deformed. It has not come back to its original position. So if that force crosses, then that particular stress is what is called as, is said to be beyond the elastic limit. Okay. So based on this elastic limit concept, there is an important law that we are going to see, which is called as Hooke's law. Hooke's law, and we are going to see modulus of elasticity. Okay. So I want everyone to write this. This is a very, very important point. So first, I'm going to give you the statement for Hooke's law. So statement for Hooke's law is like this. Within elastic limit, underline this. Within elastic limit, stress is directly proportional to strain. Guys, am I clear? So within the elastic limit, stress is observed to be directly proportional to strain. So you can write it like this. Stress is directly proportional to strain only within elastic limit. So what exactly this means is, see, I'm just using the numbers for example purpose. Okay, don't take them as exact numbers. Try to understand. Let's say I have applied a force of 2 Newton, okay, or else I will put it like this. I have applied a force of 1 Newton on an area of 1 meter square. So what is the stress that is being applied on this material? So what is the stress that I'm applying on this material? It is 1 Newton per meter square, because force by area is stress. Now what will happen is, when stress is being applied on an elastic material, let's say its length is increasing. Okay, let's say its length is increasing. So when I apply a force of 1 Newton, or when I apply a stress of 1 Newton per meter square, I can observe that, let's say, the length that is increasing is 0.5 units. Okay. Then if I increase the stress to 2 Newton per meter square, then what should have been the proportionality range that should increase here?
1.
Yes.
Sir.
So it will become 1 unit. If I increase it to 3 Newton per meter square, if it is going to become 1.5 unit. Now see, these are just examples, okay? Now let's say I'm applying like this. I have applied 10 Newton per meter square. I observed it to be, okay. I need to take continuous numbers. Observe. 4 Newton per meter square, 2 units. 5 Newton per meter square, 2.1 unit. So what has happened? Till we applied a stress of 4 Newton, the strain that was happening, okay, strain doesn't have unit, right? So you understood what is that 0.5 unit? 0.5 unit is the increase in length, the change in dimension that has taken place. Okay, I will remove this unit. So now trying to understand, because strain does not have any units associated with it. You're able to understand? So when 1 Newton per meter square stress is applied, the strain that is occurring is 0.5, 2, 1, 3, 1.5, 4, 2. What is happening at 5? What is actually expected?
2.5 is expected.
2.5. Let's say it is becoming 2.6. Then what is that? Is it proportional?
No, sir.
No. So this is the maximum stress till which I'm able to maintain the proportionality. This maximum stress is what is called as elastic limit. So if you observe, within the elastic limit, that is between 1 to 4, which is the elastic limit, you can observe that the stress is directly proportional to strain, beyond which what will happen is it will get deformed. And that law is what is called as Hooke's law. Guys, am I clear? You're able to slightly visualize what it is. So when I remove the proportionality symbol, I need to introduce a constant. So stress is equal to constant into strain. And this constant is what is called as modulus of elasticity, or it is also called as coefficient of elasticity. Okay, and that constant is given as stress divided by strain. So write it down.
Sir, can you explain which is the constant in that figure? Sir?
Called modulus of elasticity.
No, sir. Can you explain which is the constant in that figure, in that iron rod which you drew?
So see, there is a lot of noise from your side, Mithun. I'm not sure what it is. Are you using any headphones?
No, sir. I'm talking directly from PC, sir.
You're talking. See, I think some UPS sound or something is getting picked up. A lot of noise is coming. Can you just get a headphones and come? You can just plug in headphones and speak.
Sir.
I'm not able to hear you. That's the problem.
So for this example,
Which example?
in this example, the constant is 0.5 within the elastic limit.
Is it point for you? Tell me. What did I say the constant is? It's stress by strain. You are doing strain by stress. This is stress term. Stress is Newton per meter square. This is strain. So stress
So
divided
it's
by
2,
strain,
sir.
it is 2. The constant is 2 Newton per meter square. And that constant is what is called as modulus of elasticity.
Understood, sir.
Okay. Now we will give a definition to it. Mithun, are you there?
Sir?
It's still the issue is there. I'm not able to hear. Just figure that out. No, there is a lot of noise. I think people who are using earphones will have some effect on their ears. So
Yes,
please figure that out. Okay. So next is, we need to see what is the definition of modulus of elasticity. Okay, this is another important point. So you guys tell me now. You're able to see a definition. The constant is what I called it as modulus of elasticity, right? So I'm calling it as stress by strain. Can you give a definition to it? It is, so modulus of elasticity is a ratio. So when something is written in the division form, it's a ratio. It is a ratio of whom?
Stress and strain.
Ratio of stress and strain under what scenario? Is it always? What is the important word I underlined?
Within the elastic limit.
Yes, never forget it, okay? All these things, all these constants will exist only within elastic limit. Ratio of stress and strain within elastic limit is what is called as modulus of elasticity. So what is going to be the SI unit of it? It is Newton per meter square, because stress is measured in Newton per meter square. Strain is dimensionless. So Newton per meter square by 1 is Newton per meter square. Right? Next. So based on the type of stress and strain, okay, based on the types of, I can say based on the type of strain, on the basis of different types of strain, modulus of elasticity is classified as first. Okay, so listen to this carefully. The first one is called as Young's modulus of elasticity, which is represented by the symbol Y. Okay. The second is called as bulk modulus of elasticity, which is represented by a symbol called, it is not K, it is a Greek letter which is called as KPPA, which is called as kappa. Okay, not kappa, it's kappa. It's a Greek alphabet. And the third type of modulus you will be defining is called as modulus of rigidity or shear strain. Sorry, shear modulus, not strain. It's called shear modulus, and it is represented by a symbol like this. This is also a Greek letter called as neta. Like you have alpha, beta, gamma, delta, right? Like that, neta is one of the Greek letters. So based on what? On the basis of different types of strains, modulus of elasticity is classified as Young's modulus of elasticity, bulk modulus of elasticity, or third is called as modulus of rigidity. Don't get confused between them. So the type, one of the types of modulus of elasticity is modulus of rigidity. The other name for modulus of rigidity is shear modulus. Why it is called modulus of rigidity is because this constant, the third one, is mainly defined for solids, rigid substances. Okay, as I told you, the main application of this chapter that you're learning is for civil engineers. Okay, those who are into material science, if they have to construct something, they have to check the strength of a material. These are all the parameters they take into consideration. Okay, so let's look at them one by one. So I'm starting with first one, which is called as Young's modulus of elasticity, which is represented by the symbol Y. Okay, so it is represented like this. Listen to this. Every statement starts like this: within elastic limit, ratio of longitudinal stress to longitudinal strain is called Young's modulus. So within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called as Young's modulus. So you write it like this: Y is equal to ratio of longitudinal stress by longitudinal strain. Okay, in which scenario? Within elastic limit. Okay, so Y will be equal to longitudinal stress, the formula is F by A. Longitudinal strain, the formula is delta L by L. So this will also be equal to F into L divided by A into delta L. So this will be the formula: Y is equal to F into L divided by A into delta L.
So here L is length, no sir.
L is length. L is the original length. Delta is L is the change in length.
Okay.
Okay, I will draw the diagram and show. See. this is mainly used for wires. And this is the important of all, because this is what we are going to concentrate in this chapter mainly. Okay. This is L. Okay.
And A is cross-sectional area here, sir.
Yes, that's right. By now you should have understood what is that area. The circle at the bottom of the wire, that's called as cross-sectional area A, and force is applied in this direction.
Yes, sir.
Now you are able to understand?
Yes, sir.
Good. So make a note of this diagram also. See, generally what should happen is when a wire is getting extended, you would have learned this in your current electricity problems. Remember, R is equal to rho into L by A. You know this formula, right? Resistance is equal to resistivity into length divided by area. So generally they will ask, when the length increases, what will happen to the resistance? What will we do? When the length increases, we will take R is directly proportional to L. So if I say, for example, I say something like this. If the what will happen to the resistance if the length is doubled? Will the resistance also get doubled?
Yes, sir.
Actually, it will not get doubled. It will get increased 4 times. Why?
Because area will reduce by half.
Because area will decrease, no? But here, why I'm trying to relate to this concept is because it's related to length. Similarly, here also, if I have a wire, what should have actually happened? When I say there is a change in length that is taking place, then the area should have decreased, right? But what I've done is in both the cases, see, my diagram says that the area is the same. So what you're trying to do here is the extension in that wire has taken place in such a way that it is very, very small. Okay,
So
but in
del L
reality,
is very small, sir.
del L will be a small value. Okay, what we are trying to see, actually what should have happened is why we are saying when length is increasing, area is decreasing, because the volume of this material is conserved. So initially, if its volume is 1 meter cube, after extending also it should have been 1 meter cube only. You're able to understand. But in the case of Young's modulus, we are ignoring it. So I just wanted to make that point even, because you should not get this question: why is area not decreased? Del L is,
I have a doubt.
yeah, tell me.
Then can we say del L is a bit negligible value?
That's what I meant. No, del L is negligible. Then you cannot observe it very keen, because if you have to take this area also decreasing into consideration, right? That time Young's modulus is actually not the right quantity. There is something called as Poisson's ratio that we will see at the end, but that's unfortunately, I don't know why they have removed it from the where Poisson's ratio is actually removed. But I'll just explain. It's not a very big concept that it needs to be skipped. At that point, I'll explain. Okay.
Yes.
Just remind me at that point. So when you're dealing with, the moral of the story is when you're dealing with Young's modulus, the area of the material will not change. So what is going to change? It's only length. The strain, the type of strain that comes into existence is longitudinal strain. Am I clear, guys?
Yes, sir.
Yes. So what will be the SI unit of this? SI unit will be Newton per meter square, or you can also call it as Pascal, which is PA. Okay. And the dimensional formula obviously is going to be ML minus 1 T minus 2. Now see, this is the most important concept among the three, because problems will be generally asked from this concept only. We'll do an example problem to understand this concept. Okay. So write down this question. First, length of a suspended wire increases by 10 power minus 4 of its 10 power minus 4 of original length when stress of 10 power minus 7 Newton per meter square, sorry, 10 power 7 Newton per meter square is applied on it. Calculate Young's modulus of the wire. Wire means Young's modulus is defined for the material of the wire. Actually, the question will be calculate Young's modulus for the material of the wire. So for a given material, Young's modulus is always a constant. Means if you're using, let's say, a steel wire, for that steel wire, Young's modulus will always be a constant. It will not be changing according to its length or something. Okay. So how to solve? So here, one thing, though it is not mentioned in the question, we need to assume that it is happening within the elastic limit. So within the elastic limit, Y is equal to stress by strain. Stress is how much? 10 power 7 divided by strain is 10 power minus 4. It will be 10 power 11 Newton per meter square. Right? So it's a simple problem. So just a minute. Now see. So this is an NCERT based problem. Let's try to understand. So there is a structural steel rod, okay, which has a radius of 10 millimeter. When they say radius, it is a cross-sectional radius, the radius of the cross-sectional area, and length of 1 meter. A 100 kilonewton force stretches it along its length. Calculate the stress, elongation, and strain on the rod. Given that the Young's modulus of the structural steel is 2 into 10 power 11 Newton per meter square. Okay, let's try to analyze what it is. So you have a steel rod of length, how much value? So length is how much? 1 meter. So 1 meter let's call the extension as delta L. This delta L is happening due to what? Due to a force of 100 Newton being applied and area of cross section being A. So calculate the stress. Now comes the question. So when I say area is A, here area is not given, rather radius is given. So how do I take that area as? So A is equal to pi r square.
Yeah, square.
So still, yeah. So 100 Newton, kilonewton. So 100 into 10 power 3 Newton, the whole divided by area is pi r square. That is 3.14 into 10 into 10 power minus 3, the whole square. Right. So I get these many. I'll get the value of stress from here. So once I get stress, that's what they asked in the first part. Once I get the stress, how do I find the elongation? I can find the elongation by using the Young's modulus formula. So Young's modulus is given as 2 into 10 power 11 Newton per meter square, correct? But what is Y? Y is equal to stress divided by strain. So what is the value of stress? You would have found it from here. Let's say the stress is coming out as X. So X divided by strain is going to be delta L divided by L is 1 meter and Young's modulus is known. So the known quantities are Y, X and this 1. So you can find delta L from this. Here, calculation part I'm leaving it to you. Here if you observe, as I mentioned, look at the value of delta L. Delta L is 1.59 millimeter. And what is the original length of the wire? It is 1 meter. So on a comparative basis between 1 meter and 1.59 millimeter, can I say that delta L is very small? Are you guys able to understand? So that speaks about the strength of the material. Okay. Once you find this delta L, how will you find the strain?
Del L by
Del L by L. Find it, you will get the answer. But what have they asked? They have asked strain on the rod. So they have reported strain in terms of percentage. So mark this as important problem. You can try it again.
So this is in the study material, yes.
There also you will have. I think it's an example problem from NCERT. No, it's not the study material. I randomly took it from some book which was in front of me.
Sir, can you explain that elongation part, sir?
Yeah. See, when they have asked the elongation, no, I need to find out what is delta L. That's what is elongation. So to find delta L, you have two formulae. One is either I can use strain or I can use Young's modulus, which is indirectly related to strain. So for me to use the strain, I should have known the data related to strain from the question, but that nothing is given. Rather, the Young's modulus is given. So what is Young's modulus that is given? That is 2 into 10 power 11 Newton per meter square. Right? And we have calculated the stress also. Stress comes out to be 3.18 into 10 power 8 Newton per meter square. Delta L is what? L is equal to 1 meter. So Y stress delta L and L, what is the formula? Y is equal to stress divided by delta L divided by L. So you know Y, that is 2 into 10 power 11. Stress is 3.18 into 10 power 8. Delta L is what you need to find. Length is 1 meter. So one unknown, one equation, you can solve it.
Okay, sir.
Yeah. Guys, am I clear? Let's do one more problem. So what is a percentage increase? What is the percentage increase in the length of wire of diameter 2.5 millimeter? So example 4, R is equal to 2.5 millimeter, that is 2.5 into 10 power minus 3 meter. Percentage increase in the length of the wire of diameter stretched by a force of 100 kilogram weight. So force is 100 kilogram weight. Remember, 1 kilogram weight is equal to 9.8 Newton. Okay. So 100 kilogram weight will be 980 Newton. Have this in your mind. So Young's modulus of elasticity of wire is, how much is it? 12.5 into 10 power 11. It is dyne per centimeter square. Be very careful with this. Okay. So they're asking the percentage increase in the wire, right? That is delta L divided by L into 100 is called as percentage increase in length. Okay. So how to find delta L by L? Again, use the same formula. Y is equal to stress by strain. So to find the stress, you have F by A. Strain is delta L by L. So Y is 12.5 into 10 power 11. 1 dyne is how many Newton? 10 power minus 5. 1 centimeter square is 10 power 4. Sorry, 10 power minus 4 meter square is equal to F by A. F is 980 divided by area is what? Pi r square. That is 2.5 into 10 power minus 3 the whole square. The whole divided by delta L by L. So find out delta L by L. Multiply the delta L by L into 100. That will give you the answer.
Sir, can you explain what is the 2.5 into 10 to the power minus 3 the whole square?
Pi r square. Area. Force by area. The same thing like what I did in the previous problem.
So how force became that Newton value, sir? How did you convert the kg into Newton, sir?
I told you, no, here 1 kilogram weight is 9.8 Newton. Mute yourself.
So should we take pi value as 22 by 7 or 3.14 in this?
Huh?
Should we
You can take
pi?
you can take 3.14 also. That calculation part you can do it later. You need not sit now and waste the time. If the concept is clear, we can proceed to the next concept. Okay. So the next I'm going to explain is called as bulk modulus of elasticity. It is represented by kappa. So write it down. Within elastic limit, ratio of hydrostatic stress, that is a volume stress, hydrostatic stress to normal stress, volumetric strain is called bulk modulus. So within elastic limit, ratio of hydrostatic stress to volumetric strain is called as bulk modulus of elasticity. So remember, this hydrostatic stress is also called as pressure. Remember this is an important concept in thermodynamics. Like how you learn thermodynamics and chemistry, we'll be seeing in physics also. So at that point, I'll be using this term. Okay. So kappa, we can write it as pressure divided by volumetric strain is delta V by V. But remember, when an object is like this, hydrostatic stress means, revisit the definition, it says, if the force is applied perpendicular from all the directions, and how should it be applied? It should be applied normal to the surface. Then that particular stress is what is called as hydrostatic stress. So when you apply the force equally from all the directions, then you can see that the volume of the material will decrease. Okay. So pressure divided by delta V by V. I'm using a negative sign here. Why am I using negative sign? Because delta V is negative. Volume has decreased. Okay. So this kappa is equal to pressure divided by minus delta V by V is what is the mathematical formula for bulk modulus of elasticity.
Could you explain again why it's minus del V by V?
Because volume decreases. Since pressure applied will compress the object, it will not expand. Compress the object, delta V is negative. Got it? So the reciprocal of bulk modulus is called as compressibility. It's called reciprocal of bulk modulus of elasticity. So compressibility will be like this. 1 divided by kappa. So 1 divided by kappa is what is called as compressibility. Okay. So the next one is shear modulus of rigidity, that is removed. Elastic energy is removed. Elastic behavior is also removed. That is the graph. So this chapter is actually over. According to deleted portions, yes, it is over. Okay. So if they ask question related to bulk modulus also, you have to do the problem in a similar way like how you did in the case of Young's modulus. But 99.9% no question will be asked on bulk modulus. Everything will be related to Young's modulus only. Am I clear, guys? Is there any doubt?
No, sir.
So
Sir, can you just show the previous page,
for
sir?
today, actually, we can wind up. Tomorrow, I'll start the new chapter. That is mechanical properties of fluids. Okay, so tomorrow's topic will be mechanical properties of fluids. And the test, please make a note of this. This week test is Sunday. What is the date, guys? 8th. You will have work, power, energy, and rotation mechanics. On 15/11, you will have, sorry, not gravitation. You will have the cumulative test. Actually, I forgot to post this officially, but today we'll get a message. So, work, energy, power, and rotation mechanics, morning 10 to 11:30 a.m. Cumulative test is from 9:30 to 12:30 a.m. This is for 70 marks and this is for 35 marks.
Sir, Diwali, sir, 15th.
When the 15th, right?
Yes, sir.
Okay, we can have the week next to it. You will have enough time to prepare also. 20 to 11 p.m.
Cumulative 70 marks, no, sir.
Yes, because it's complete first volume, right? Cumulative means it's complete first volume. You have enough time to study. Don't come up with excuse. Today date is only 2. You have 20 days time, solid 3 weeks to prepare. Okay.
Okay, sir.
That's it. I hope you guys made a note of this. So that's all for today. Tomorrow's class will start mechanical properties of fluids. Wait a minute, don't leave.